Assalamu alaikum and welcome to Mathcast with Faria Yusuf. And the next chapter that we shall be starting in this video is circular measure. Before starting circular measure, there are a few terms which one needs to understand. First term here is radian, and what is a radian? We will be doing the definition with respect to 1 radian here. So 1 radian is the angle subtended at the center of a circle, radius r. So if this is the center of the circle with radius r on both the sides, so it's the angle subtended at the center of a circle radius r by an arc equal in length to the radius of the circle, So this is the arc length which should be equal to the radius of the circle to give us a 1 radian. So radian is basically a measure for the angle subtended by the two radii starting from the center of the circle. Now, degree and radian conversion. Usually angles are measured in degrees. Now, if we need to convert degrees to radian, or if we need to know the conversion between the degree and the radian angle, then we should know that 180 degrees is equal to pi radian. 180 degrees equals pi radian. Therefore, I should say that 360 degrees should be equal to a 2 pi radian here. So let's convert an angle. Let's take the example as 60 degrees to the radian angle. So if we know that it's 180 degrees which is equals to pi radian, then to find the conversion of 60 degrees to radian, I should say that it's 60 times pi by 180, giving me a pi by 3 radian, meaning 60 degrees shall be equal to pi by 3 radian here. So here you should know that if you are asked to convert a degree angle in the radian mode, just multiply the degree angle by pi by 180 degrees. So this is when you convert a degree to the radian angle, then just multiply the degree angle by pi by 180 degrees. Let's do one more example, and let's say that now they are asking you to convert 150 degrees to the radian angle. So to convert 150 degrees to the radian angle, you should know that you have to multiply 150 by pi by 180 degrees. And then I should see that here I should be getting a 5 pi by 6, which is the conversion for 150 degrees to the radian, and 5 pi by 6 is going to be my radian angle here. Let's do the opposite, and let's say that here you need to convert 2 pi by 3 to the degree mode. So to convert 2 pi by 3 to the degree mode, so you need to multiply the radian angle by 180 divided by pi, meaning in this case I should say that it's a 2 pi by 3 which should get multiplied by 180 divided by pi. The pi here gets simplified and you will be left here with 120 degrees. So this is going to be the answer for the conversion of 2 pi by 3 radian to the degree angle, which is going to be 120 degrees here. So let's convert 3 pi by 4 radians to degrees, and here again I should know that I need to multiply 3 pi by 4 by 180 divided by pi, and simplifying them I should be getting here 135 degrees. So this then shall be my answer for the conversion of 3 pi by 4 radian to degrees as 135 degrees, and the conversion of 2 pi by 3 radian to 120 degrees here. So there are these angles which one should be knowing by heart. You should be knowing them and also learning them by heart. That for 0 degrees the radian angle is going to be 0 radian. 30 degrees it should be a pi by 6 radian. 45 degrees is a pi by 4 radian, 60 degrees is a pi by 3, 90 degrees is a pi by 2, 180 degrees is a pi, 270 is a 3 pi by 2 radian, and 360 degrees is equal to a 2 pi radian. These are very important angles, and it will save a lot of time if students know these radian measures by heart. So this is one thing that we need to know about the radian values. And then before starting circular measure, there are few concepts of trigonometry also which we need to revise here. So let's do them also. Now for trigonometry, first thing is that for right angle triangles, let's call this as A, B, and C. And let's say we have the theta angle here. So with respect to the theta angle with AB, I will be calling it as the adjacent or as my base side. And the angle opposite to theta, I shall be calling it as a perpendicular, or I shall be calling it as an opposite. And the angle and the side opposite 90 degrees, obviously that needs to be called as our hypotenuse. So with respect to this right angle triangle, I should know that my sine theta shall be equal to opposite over hypotenuse, or I can also say that this is a perpendicular over hypotenuse. Cosine theta shall be equal to adjacent over hypotenuse, or I can say that this is going to be base over hypotenuse. And our tan theta, we can say, is equals to opposite over adjacent. Or we can also say that this is going to be the perpendicular over the base. So the best thing to remember, the three trigonometric ratios for right angle triangles are SOHCAHTOA, where we say that we have sine opposite hypotenuse, then we have cos, which is equal to adjacent over hypotenuse, and we have tangent, which can be represented as opposite over adjacent. So this is going to be SOHCAHTOA, which one should be knowing very well. If we have a triangle which is not a right angle triangle, like we have this triangle over here, it's ABC. So we know that opposite this angle, which is written in capital A, I will be showing the side length as small a. Opposite B, I will be showing the side length AC as small b. And opposite C, I will be showing the side length AB as a small c. So this area of this triangle, it can be given as a 1 by 2 into the two adjacent sides A and B and the inclusive angle and the sine of the inclusive angle C. Two adjacent sides AB, the product of AB into sine of angle C here. In the same manner, I can also take half into B and C, the two adjacent sides, into sine of the inclusive angle A here. Or I can also say that this is going to be 1 by 2 into AC into sine of the inclusive angle, which is B over here. So this is how I can find the area of a triangle which is not a right angle triangle. Even if it is a right angle triangle, then we know that substituting sine of 90 degrees, we know sine of 90 degrees is equal to a 1, and I will only be left to the two adjacent sides, which are the base and the perpendicular here. So it's for right angle triangle, it's half into base into height only. Another thing is the ratios. We have the sine rule, sorry, not the ratios, but the rules. If we have for the sine rule, we know that the sine rule is given by the opposite angle and side. Therefore, I can say it's small a, the side length a, divided by sine of a, which shall be equal to b divided by opposite angle, which is sine of b. And this also will be equal to c, this c divided by the angle sine of c over here. So it's A over sine of A, which equals B over sine of B, and that equals C over sine of C here. The cosine rule. For the cosine rule, it's given as A square, this A square, which is then equal to, now just remember, sine rule deals with opposite angle and sides, whereas for cosine we go with the two adjacent sides. Meaning if we are supposed to find out A, then we should say that A square equals B square plus C square minus twice of the product of BC into cos of the inclusive angle, which is going to be A here. In the same manner, B square shall be equal to A square plus C square minus twice of AC into cos of the inclusive angle between AC, which is a B here. And then C square, it shall be equal to A square plus B square minus twice of AB cos of C. Rearranging the cosine rule, I can find the angles also, and doing that I can say it's cos of A, which is equals to B square plus C square minus A square divided by twice of BC, or cos of B shall be equal to A square plus C square minus B square divided by twice of AC, and cos of C equals A square plus B square minus C square divided by twice of AB. So this is a little bit of trigonometry which we should be knowing before starting circular measures here. So let's start circular measure. So starting circular measure, let's say we have this circle here with center as O, center O, and the radius which equals R. This is my radius, and the radius here which equals R. And this radius is obviously going to be up till the circumference A, the point on the circumference here which is represented as A, and the point on the circumference here which is represented as B. AB is the arc length. AB is part of the circumference of the circle which represents the arc length and is given as S AB, arc length AB. And we can say that S is the arc length, and by formula it is given as R theta, where R is the radius and theta is the angle at center measured in radians. So S equals R theta, radius times the angle at the center subtended by the two radii, and this theta has to be in the radian measure. So this is going to be the arc length formula. And what if we have to get the area of the sector? This region here that we have just formed in the shaded as green, this is called the sector of the circle. Sector of the circle from the center up till the circumference, and we have the arc length here. So for this simple sector, I should say that the area of this sector, the area of the sector is going to be half R times the arc length S. Or if we substitute S as R theta, then I should say that this area has to be 1 by 2 R into R theta, or I can say that this area of the sector can be written as a 1 by 2 R square theta. So this is going to be the area of the sector where the theta is measured in radians. Arc length R theta and area equals half R square theta, where we have to be very much particular that our theta has to be in the radian measure. So this is what is our circular measure here. So let's do a simple question to solve for circular measure. So question 1 says OAB is a sector of a circle. OAB, it's a sector of a circle with center O and a radius of 12 centimeters. So it's a radius of 12 centimeters, meaning OB also has to be a 12 centimeters here. OB, it also needs to be a 12 centimeters because the radii in a circle remains the same. So we need to find, number 1, the perimeter of the shaded region. So for the perimeter of the shaded region, what I can see here is that this shaded region has the chord AB and the arc length AB. We have this chord AB and we have this arc length AB here. That shall give me the perimeter of the shaded region. So for part A, solution A, I can say that it's the perimeter which shall be equal to the length of the chord AB and then the arc length AB here. So it's very easy to find the arc length. I can say that the arc length has to be r theta. Theta is already given in the radian measure. So radius is a 12 times a pi by 4. So I can say that this arc length is going to be a 3 pi. So I have the arc length which shall be equal to a 3 pi. To find AB, so to find AB, what I can see here is that AB is giving me a triangle for which we know the two adjacent sides. It's OAB and OA and B here. We know the two adjacent sides, they are 12, and we know the angle here, which is a pi by 4. So applying the cosine rule, I should say that it should be AB, which should be equal to under root OA the whole square plus OB the whole square minus twice of OA and OB into cos of pi by 4 here. So this then will be equal to 12 the whole square plus 12 the whole square minus 2 into 12 into cos of pi by 4, which is a 1 over under root 2 here. So solving it, I will be getting the length of AB, the chord length AB, and this is then going to be 9.18 centimeters, 184 centimeters. So we have the arc length and we have the length AB, which is 9.184 centimeters. So we can now say here that the perimeter here is going to be AB, which is 9.184 plus the arc length, which is a 3 pi. So plus 3 pi, that will give me the answer as 18.6 centimeters. So the perimeter here comes out to be 18.6 centimeters. So this is how we should be finding out the perimeter of this sector, which has a segment, which has a shaded segment here. Now part B says find the area of the shaded region. So to find the area of the shaded region, we know that this is the shaded region here, which we are supposed to find out. So what I can see here is that out of the entire sector that we have, only if I am able to subtract the area of the triangle, this triangle which is OAB with respect to the chord length which is AB, then I should be getting the area of the shaded region here. This is the area which is shaded and we need to find out this area. So to do that, I should say that area shaded is actually equal to the area of the sector minus area of the triangle OAB. So let's find the area of the sector. So to find the area of the sector, we know the formula. It should be half r square theta, or I can say here that this shall be equal to half radius is a 12, so it should be a 12 square theta. In the radian mode, it has to be a pi by 4 here. So this area sector then comes out to be a 56.549 centimeter square. So this is going to be the area of the sector. Let's find out the area of the triangle. So to find the area of the triangle, I should say that area of the triangle is given as half into the radius into sine of theta here. Or here I should say it's 1 by 2 into 12 the whole square and sine of pi by 4. So solving it further, I should say, so this area triangle, it will come out to be a 50.912 here, centimeter square. So area for the shaded region then is going to be area sector, which is equal to a 56.549 50.549 minus area triangle, which is 50.912, and this answer then comes out to be 5.637, or in three significant figures, I can say that this shaded area is going to be a 5.64 centimeter square. So this is how we will be finding out the area of the shaded region for the given sector here. The next question is from Winter 2010, paper 1, variant 1, and it's question number 9 in the paper. So the question here says that the diagram shows two circles, C1 and C2. The bigger circle is C1 and the smaller is C2. Touching at the points T, circle C1 has center P and the radius 8 centimeters. The radius PR, the radius PT, that is 8 centimeters. Circle C2 has center Q and the radius 2 centimeters, meaning QT and QS, they need to be 2 centimeters. Point R and S, they lie on C1 and C2 respectively, and RS is a tangent to both the circles. So tangent to both the circles, just remember the property which says that tangent to the radius, tangent and the radius, where the radius meets the tangent, then the radius and tangent, they will always be perpendicular to each other. So this radius and the tangent perpendicular to each other, this radius and the tangent, this is also going to be perpendicular at point S here. So this is a very important property to remember, that radius and tangent, they are always perpendicular to each other, meaning they should be making 90 degrees with respect to each other. Part 1 says, show that RS equals 8 centimeters. From R to S, this should be equal to 8 centimeters. So from R to S, if we have to show that this shall be equal to 8 centimeters, then with respect to RS, if I draw this line, which is just parallel to RS, let's call it UQ, then UQ shall also be equal to 8 centimeters, meaning if I get to prove here that UQ is 8 centimeters, then it will mean that RS will also be equal to 8 centimeters. So let's start working on it. So if you look at this triangle, if you look at this triangle with respect to QU, then we can see here that QS equals a 2 centimeters, this being perpendicular, both QS and UR at 90 degrees. We can say that UR is also going to be 2 centimeters. That means PU shall be 8 minus 2, giving us 6 centimeters. So if we look at this triangle PUQ, if we look at the triangle PUQ, then we can see that here PU, meaning the perpendicular here, shall be equal to 6 centimeters, shall be equal to 6 centimeters, and PQ shall be equal to 8 centimeters here. So this is the right angle triangle that we have made, showing that PU is 6 centimeters and PQ then PT then shall be equal to 8 centimeters here. PQ then shall be equal to 8 plus 2, that equals 10 centimeters. So 6 centimeters is my perpendicular and PQ is 10 centimeters. That means to find the base, I should be applying the Pythagoras theorem. And with respect to the Pythagoras theorem, I should say that it is 10 square, which should be equal to perpendicular square, that means 6 the whole square, plus UQ the whole square, that is base the whole square. So we are applying the Pythagoras theorem. 10 square is 100 minus 6 square, which is a 36, equals a UQ square. UQ square is a 64, and further I can say that it's RS, which is equals to UQ, that is equals to square root of 64, and square root of 64 becomes an 8. Therefore, we have shown here that RS is equal to 8 centimeters. Moving to the second part. The second part says Find the angle RPQ in radians. Find the angle RPQ in radians correct to four significant figures. R, P, and then Q. RPQ, that should be equal, that we should be finding out correct to four significant figures here. So RPQ up to 4 centimeters, what we can see here is that we were already solving part 1 with the right angle triangle in which we had PU and Q. So with respect to PU and Q, they are basically asking for this angle at P. So if they are asking for this angle at P, then I should say here that it should be our base here. It should be our base here, which is PU. Then it should be PQ, which equals a 10 centimeters. With respect to the adjacent and the hypotenuse, I should be having cos of RPQ, which equals adjacent 6 divided by the hypotenuse, which is a 10, or we should say it's cos inverse 3 by 5, or cos inverse 3 by 5 in the radian mode shall be equal to, just remember we have to get it up to 4 significant figures, so I should say that this should be equal to 0.9273 radians. So this is then going to be the answer up to 4 significant figures here, 0.9273. The third part says find the area of the shaded region. Now, area of the shaded region, this is our shaded region here. So to get the area of the shaded region, what I can see here is that PR, S, Q, and then P, this is actually making a trapezium with PR and QS parallel to each other and RS being the height between the two parallel sides here. So if we should be finding out the area of the trapezium, and from this area if I subtract the area of the sector PRT and the sector QTS, only then I will be able to get this shaded area. So let's start working on it also. So we have discussed that the shaded area is equal to area trapezium minus area sector PRT minus area sector QTS. So we have this diagram in front of us. We have the area of the trapezium from which we shall be subtracting sector PRT and sector QTS. So area of trapezium shall be equal to 1 by 2 into sum of parallel sides. The parallel sides are PR and QS. That means it should be 8 plus 2. So 8 plus 2 times RS, which is going to be 8 centimeters. So solving it, I am getting the area of trapezium, which equals a 40 centimeter square. Let's find the area of the sector PRT. So area sector PRT, sector is given as half r square theta. The radius here is 8 and theta we found out in the previous part, and this theta was equal to 0.9273. So this was a 9273 here. So solving it, I should say that this area comes out to be 1 by 2 into r square, which is an 8 square into 0.9273, and that should give me the area, which shall be equal to 29.673 centimeter square. In the same manner, we shall be finding out the area of the sector QTS. To get the theta value, I should be having the angle at Q with respect to the two radii QT and QS. To find that angle, I know that UQS, that's a 90 degrees, to find, or a pi by 2 radian, and to find PQU, I can say that UQP, UQP, UQ, and then P, this angle here, UQP can be equal to pi by 2 minus 0.927 and 3 here. So pi by 2 minus 0.9273, that is going to give me 0.6438 radians. So UQP is a 0.6438 radians, and to this, if I shall be adding a pi by 2, then this answer I'm getting here is 2.215 radian. So 2.215 radian here. And then with respect to that, I have this angle TQS. That means now I should be able to find out the area of the sector TQS, for which again I shall be applying the formula half r squared theta. The radius is a 2 here, so I'm saying it's 1 by 2 into 2 square into the theta value TQS, that is 2.215, and then I'm getting the area sector, which is 4.429 centimeters square. So to find the shaded area, we have the complete data now. We just need to substitute that data in the formula, for which we said it's area trapezium minus area sector PRT minus area sector QTS. That means it should be 40 minus 29.673, which was the area of the sector PRT, minus 4.429 area sector QTS, and the area of the shaded region here then comes out to be 5.898, or up to three significant figures, we should say it's a 5.90 centimeters square. So this is one question from circular measure, and we shall be continuing this practice from past papers in the next video. So see you there, inshallah. Allah Hafiz and take care.